So that's extremely useful concept. You should be able, this is really related to some earlier things about op-amps. This concept will have been examined these topics have been examined in the mid-semester. You may expect similar things on some more complicated op-amps, or op-amp circuits in the final exam. So we know how to deal with differential and common mode signals, and later on, towards the end, we'll get bridge circuits. Yeah, we'll talk about it in a moment. So from specialty amplifiers, differential and common mode signals are definitely important. And difference amplifiers, again, it's just application of something that we've done already. We studied earlier in the semester. Transfer functions, very, very important. I already mentioned that. So remember, you can get from transfer function, you can find everything you want about the circuit. If you look at, say, any transfer function, it's always a ratio of two polynomials in S. Okay? Even if one polynomial is a degenerate polynomial like a number, it's still a polynomial, just order 0. Okay? So because it's a ratio of two polynomials, each polynomial may have its own roots, and the roots of the numerator are called zeros of the transfer function. The roots of the denominator are called poles of the transfer function. So especially analyzing the poles allows you to find the natural response of the system straight away, because the poles of the transfer function determine the natural response. In fact, poles of all transfer functions will be the same. Well, they have to be, otherwise we would describe two different circuits. Okay, so if it's the same system, the transfer function may have the same, must have the same denominator. Then from the transfer function, if you can find force response very easy by simply looking at what the input is and finding for particular input, finding the value of S. It could be, it would not, in general it's sigma plus j omega, but it could be just sigma, could be just j omega, could be 0. Okay, so whichever it's the case, you plug it into a transfer function, you get the response straight away without too much calculations. It's pure algebra instead of solving differential equations. It's much better solving algebraic equations than differential ones. That's why people came up with transforms like Laplace transform, which exactly does that. Transforms a differential equation into or solution of a differential equation to a solving of a polynomial algebraic equation. So from transfer function you can get natural response, you can get force response, you can get complete response by just adding these two. So they are very, very useful, and definitely you will be examined on that. Bridge circuits are very simple resistive circuits, but they are very, very important. Okay, so you don't have to know everything about the measurements and where they are used and so on, but you should be able to analyze a bridge circuit if you get one. Okay, and the final lecture was on system modeling. Again, you should be able to see blocks, simple blocks to decompose a larger system into simple blocks, and then each block will have its own transfer function, And then, of course, you can easily combine those individual small building blocks, transfer functions, into a total transfer function. So that's really all about the revision. There's a number of things that I sort of remember students are very anxious about. Like, for example, I just saw the next thing here, matrices. So please remember that in the final exam, I will never ask you to solve more than 2 equations. Okay, so if you have a circuit and you write down those equations of that circuit because you have to solve them, if you get more than 2, you should know you are on the wrong track. Okay, you started in the wrong direction. There will never be more than 2, and because I don't think it's useful to do this kind of stuff in the exam. So you have to be able to solve 2 equations, but by hand, but no more than 2. So this is very useful. It's always, if you have even 2 equations, it's useful to actually use matrix notation. It's just easier to manipulate the numbers. It's very easy to find the determinant of 2 by 2 matrix. It's just 2 products, the sum of 2 products, or difference of 2 products. So it's simple, or simpler than just trying to substitute equations and use some other techniques. Also, a very useful thing is if you write the equation in a matrix form, say nodal equation or mesh equation, you can easily check if you made some gross errors, because if you look at the matrix entries, they should all be either z's or y's, depending on which analysis you apply. If you